Good day, everyone, and welcome to the Well Remediation Toolbox first webinar of 2023. I'm Jonathan Heseltine with Innotech Alberta. We have a jam-packed schedule today, so we're going to get into the technical presentations straight away. But first, a few introductory remarks. In 2021, Innotech, along with NZTC, hosted a series of webinars on new well remediation plug and abandonment technologies. And as things continue to advance and develop, we've decided to continue the series with two more webinars planned so far, this one and one in October. Next slide, please. So we have three speakers today from companies providing alternative barrier materials and enabling technologies. Each presentation will be about 20 minutes, followed by 10 minutes of Q&A. The questions will be typed in by the attendees, so your screen should look something similar to what's shown there. So you can type in your questions and I will relay them to the presenters verbally. Next slide. And to get right into it, these are our speakers today. So in reverse order, we have John Griffin, the Vice President of Sales from BioSqueeze, Peter Knight, the President of Wireline Abandonment Corp, and Mark Archibald, the Global Technical Development Manager at Italmatch Chemicals. So with that, I'd like to hand it over to Mark.
Yeah, thanks, Jonathan. Good morning, good afternoon, good evening, wherever you are joining us from. Thanks for coming along. And I've been invited to talk about an update to the Aubin Exclude. Some of you that attended previously with Innotech Alberta during 2021 may have remembered or associate Exclude more with Aubin. And I'll dive into why we are now Italmatch in a minute. Next slide, please. Yeah, so I'm going to give a quick introduction to Italmatch. I'm going to give a quick recap of Exclude for those that are maybe joining for the first time. A quick summary of what the technology is, what it does, and how it came about. Then I'm going to dive into some updates to our lab testing qualification procedures. A couple of case histories will be presented. Then I'll run through some frequently asked questions, cover some of the answers that we have, and maybe highlight some of the outstanding questions, and then a quick summary. Next, please. So as I say, some of you may be aware of Aubin, and that's how you might know the Exclude product name itself. Lindsay presented back in 2021, so any of you that were there may remember her. During 2022, Italmatch Chemicals Group acquired Aubin. Italmatch are a leading global chemical company specializing in performance additives for the range of markets that you see there. In terms of Italmatch Oil and Gas Solutions, there's a specialized team dedicated to work just on the oil and gas function and chemistry and meet the needs of the market there. And they looked at Aubin and saw that they brought something different to them. So 30 years of experience in developing reliable chemical solutions, specifically for oil field chemistry. We had a growing portfolio, including some in the renewables market, and specifically they looked at us as giving them a good footprint in the Middle East. Next, please. So the Aubin portfolio itself covers a wide range of things. I myself have come into the team at the start of the year. My background is oil field scale, which you'll see as we go through the presentation how that fits in. And that's where Aubin Exclude fits in. It's currently marketed specifically for plug and abandonment technology. We have a sister technology called Aubin XMax, which I'll also talk about a bit during the presentation, and that's targeting water shutoff, specifically zonal isolation. Aubin have a wider range of portfolio covering well services. Obviously, cementing additives is a big part of what Aubin were known for and do. They also have pipeline gels and pigs. They have a subsea arm looking at buoyancy products for renewable sector. And we also have offshore wind and waste management. Next, please. So Aubin Exclude, what is it? It's induced formation damage. So we have a calibrated mix of 3 components designed specifically to give a controlled inorganic deposition within the reservoir. Reaction is controlled until the fluids enter formation, and the fluids are easily pumped from existing platform technology and pumping systems without the need for a rig. So this makes it an ideal cost-effective way of providing plug and abandonment in wells early on without the need to go off and hire expensive or specialized equipment. The advantages of Exclude are, once it's in the formation, the scale precipitates, blocking pore throats and reducing the permeability, and it's specifically happening within the formation, not in the wellbore. So the technology is designed such that the reaction will not take place and cause a plug in the wellbore, leaving the wellbore access for other activities. We have patents filed globally to protect the technology, and the reaction, as you see, is not reversible. The scale we're forming is not easily removed and not susceptible to attack by most fluids that you would see downhole. Next, please. In terms of applications that we target with this technology, so obviously P&A is our primary target. As I say, we don't have a need for specialized equipment, making it really suitable for offshore, where it can be really expensive to hire mobile drilling units or specialized rigs to do something such as a cement job, for example. The nature of the fluids mean that we can pump it past any into wells with access issues, so anywhere where there's tools stuck, things like that, or deteriorated wellheads, or poor well integrity, so you can deploy via coiled tubing as well. We also see potential for annular cement remediation, so where you may have existing cement with pinholes, micro annuli through the existing plugs. We can use Exclude to block those up, and we can also see it as an alternative to perf wash and cement or section milling, which is the current methods for addressing issues with cement. And we also see it has some application in carbon capture and storage systems, where we may need to stop the inflow of the injected fluids into old wells or old production wells. So you might want to use Exclude as a means of sealing those off. And I mentioned already the sister technology, Aubin XMax. It's based on the same technology, but aimed at applications where we may want to continue production from other zones in the well, or where we may want to perforate new zones in a well. So you may have a watered out production zone, and we want to isolate that zone before then taking production from an existing upper zone or lower zone, or we may want to reperf and do new perforations into hydrocarbon producing zones. Next, please. So a quick summary. Exclude is mineral scale is used to create a barrier in the formation rather than the wellbore. This means we avoid the need for good annular cement as the barrier extends beyond this, and we are maintaining the wellbore internal diameter for future well work, whether that be additional operations during decommissioning to set additional plugs, or additional barriers, or for geothermal operations. We see it as a cost-effective alternative to existing technologies, in that it can be applied by bullheading into the formation without the need for a rig or through existing tubing, or it can be deployed via coiled tubing for selective zonal isolation. And it's relatively low risk. They're non-hazardous components that are used. Next, please. So I'm going to quickly talk about what we did initially in our lab qualification and during development. So this was the initial work that was used during development. Now, before my time, but I've looked back at all the work, obviously, that was done to teach myself the technology. And what I see is that they initially used static jar tests as a simple means of establishing proof of concept. So can we get the fluids to scale? Can we get some level of control in those fluids? And what they've managed to do with the jar tests alone is define the composition of the anion cation brines that are used. As I say, establish the proof of concept, and the jar testing that was done managed to suggest a likely mixing ratio and dosage rate of the inhibitor that is used to control the scale until it's in the formation. In addition to that, we'd run sandpack tests to demonstrate that we could block a porous medium. They were fairly simple and straightforward tests, nothing too technical. Basically pouring the liquids through a sandpack and seeing what happened under pressure. But there's obviously difficult to quantify from that. So we then moved on to core flood testing. These were done independently at Heriot Watt in conjunction with Oil and Gas UK. And what they managed to do in the core flood test was highlight that modifications were required to the standard core flood equipment setup. So standard core flood equipment would be used for evaluating scale inhibitors used for squeeze application generally. So we highlighted that during that test, during the testing at Heriot Watt, that they had to do some modification to the rig to how the fluids were injected more to replicate more closely what would happen in the field. But they did manage to demonstrate successful blockage within the pore space within the core, and they managed to achieve up to a 99.7% permeability reduction. Testing was only done at ambient temperatures. I'm yet to go on and look at its field-specific conditions, but that's something I'm working on. With that, the Heriot Watt had indicated that better results would be predicted in the field because higher temperatures and pressures equals more scale for the system that we're injecting. Next, please. So since coming into the company at the start of the year, I bring obviously a scale inhibitor or scale inhibitor selection and development background, and therefore the testing that goes along with that. To the process, and as this technology is specifically focused on using scale, which has been a problem for oil fields for many years, as a solution, I also bring with me a wealth of knowledge which can be useful. So I initially started with scale prediction modeling to try and determine if we had, or if they had already achieved the correct mixing ratio for the two anion cation components. I considered those, modelling those over a range of temperatures from 20 to 90 to represent a range of scenarios that we may see in wells. And what we managed to do is confirm that the mixing ratio that we had settled on initially through the jar testing was actually pretty close to optimal at a 50-50 mix, which obviously makes it easier to handle and design treatments when you're going offshore or to the location. I then moved on to take the static jar test a little bit further, and I want to look at the optimization of the scaling time and the potential mass and see how much control we could get. But the challenge we have is that the jar test itself does not actually replicate very closely what's happening during a field treatment scenario, where we have a dynamic situation during pumping followed by a static system when we move into the actual pore space. And the addition of the pore space itself in a field treatment cannot be replicated in a jar test. And that's why we'd end up moving on to the core flood, which we'll talk about again in a minute. So what we did was evaluate scaling time and potential mass, varying the concentrations of the three components to see if we could optimize the scaling that we could generate. So what those tests have done is confirm the potential for us to reduce the inhibitor dosage a little bit. So we were still getting the same level of scaling that we were seeing, and the timing we think is right for what is a jar test. We obviously need to do further testing to confirm that works the same in the field. And those tests also highlight that an inhibitor is required, because I actually thought that you could maybe just get away with taking the inhibitor out, but the inhibitor actually provides some level of crystal growth modification to promote deposition. Without the scale inhibitor there, the scale that forms very quickly, but also forms in such a way that won't agglomerate in the same way, and then therefore may not block pore spaces within the core or within the reservoir. And then I wanted to add something a little bit different, which was dynamic scaling loop tests, which again I have experience with, and anyone that's done oil field scaling and testing of scale inhibitors will be familiar with this process. It's taking the scaling fluids and mixing them together within a microbore coil, measuring the pressure across the coil, and you get a differential pressure increase as the scaling occurs. You can then add inhibitors, and it changes the time to scale up, and that shows you the performance of the inhibitors. So I wanted to see if it could be used in the same way, but also I felt that the small microbore coil might replicate, the pore space that we have within the core to some extent. And blockage of that may be controllable and variable depending on what we did with the fluid and mix that we were putting in. So could we establish a method of using a DSL to test open exclude? The reasons it's an industry recognized test, and it provides a closer replication of the deployment scenarios. So where the static jar tests only looks at a static system, the dynamic scaling loop test replicates the pumping of the fluid, so the dynamic situation where we're pumping, and then it may be possible to use to stop the flow in the system for a period to replicate shut-in during treatment, or the static scenario that we have during field deployment. So what those tests have shown me so far is the initial feasibility work has been performed. And while there are some challenges, this system scales really quickly, although there's things I think we can do to change that in terms of the conditions that we're using and the actual test setup itself. So again, I've got further work to do in that scenario, and I have yet to get the equipment up and moved up to my lab to then do that myself. Next. So as I say, we've got to expand on the DSL testing. I'm trying to get hold of a core flood capability in the lab. We are working through the business case and the CapEx just now for that. And I am also looking to try and establish a third-party barrier qualification method for acceptance by operators and regulators, because that's what we will need to take this technology forward. That's one of the questions you'll see is how do you prove it works in the field? So I think we need to establish a more robust third-party barrier qualification method over and above the core flood, which I think will be the mainstay. But for operators, larger operators and regulators, I think we're going to need a more established third-party test. So that's all the future work. Next, please. So a quick overview of status. Obviously, Exclude has been selected and is being tested by Innotech Alberta as part of their alternatives to cement for wellbore remediation and commissioning GIP. We have interest, high levels of interest from multiple parties in US, UK, Middle East and Australia. So it's got global interest and global looking on this. So far, however, we have had very few trials, very few people willing to take it to the field level. We had one lined up for the Netherlands, which has been delayed for reasons out with our control. We have had one offshore development planned but cancelled at the last minute. Again, there was some risks and things that they evaluated right at the last minute, which meant that didn't go ahead. We have had one trial in the UK onshore, which I'll talk about as one of the case histories in a minute. We have had one offshore field trial using the sister technology XMAX in Malaysia. I'll also talk a bit about that. And we have a major operator in LATAM who have placed an order and are giving us a 3-well trial, but there's some bureaucracy going ahead which is slowing that whole process down. I think we're looking at towards the end of the year for the first trial. Although it's been in the works since I first came on board at the start of the year. As you see, there's various reasons. COVID and changes in the economic climate changed the way people were looking at things, and the way that the workovers and things that they were doing, which meant that some of the field trials we had in the pipeline were postponed or delayed, alongside the high prices, which meant that focus moved to production. Next, please. So I'll go through these pretty quickly. There's not a great deal of information. First one is the onshore well in the UK. We had an operator with 100-odd old, and I mean old, onshore wells. Some of these wells were drilled over 50 to 60 years ago, and some of them hadn't been touched for over 20 years. The trial was supported by ourselves and NZTC along with the operator. And as part of the trial, we included distributed acoustic sensing and distributed temperature sensing monitoring provided by WellSense as part of the trial. So there's a quick couple of images there about the setup at the well. We initially looked at 3 wells potentially for the trial. The first well that we trialed in, though, however, didn't have any injectivity and had to be abandoned. The second well went successfully, and we kept pumping into that well until we got to the end of the trial period, and therefore a decision was made to keep trying in that well, and you'll see why in a minute. But then no attempt was made to the third well because we ran out of time after focusing on the successful injection that we got to the second well. So the treatment itself was designed for 40 feet of low perm formation at a depth, you'll see there, of 1,320 feet. But we got no pressure build up despite pumping 2,000 litres per feet of the exclude material, which should have been way more than enough. And the reason is because we had poor well integrity. We had the fluids disappearing into a hole or a gap or a space in the casing at around 580 feet, and this was identified by the thermal sensing that we were doing during treatment. So as it happened, all the exclude fluids were being lost behind an uncemented casing into a highly permeable formation at that 580 feet, meaning that none of what we were pumping in ever reached the target zone itself. So disappointing as it was, we can confirm that the trial was operationally successful and we managed to mix and pump fluids into a reservoir. Okay, that reservoir wasn't the right reservoir. The failure of the trial itself is, if you deem it a failure, is due to poor well integrity and the fluids not being placed to the target. And that was down to a number of factors, mainly because the well selection was poor and no logs, or it was a well that hadn't been looked at for years. They just picked a well and handed it over. So we hadn't had a chance to do any recent logs, which would identify the hole or the space in the casing, and meant we would have deployed it in a different manner or used coiled tubing to target it, or done something to try and block that, that zone first before we did our injection. It highlighted that data logging was crucial in understanding what was going on with the well and what was happening during treatment. And we also feel that there's a possibility possibly the need to speed up the treatment or optimize chemical to maximize scale formation in the near wellbore, depending on the permeability obviously that we're trying to treat. And then there's a potential need to reduce the volumes required for pumping, and that was what was fed back from the team doing the trial. Next, please. So the second treatment was with Albin X-Max, and this was offshore in Malaysia. What we were doing here was targeting a zonal isolation of water out perforations with the idea of isolating deepest perforations, maintaining the wellbore access, and therefore allowing for later perforation in and production from upper zones. The operator had originally planned to do the treatment in 2021 and had actually purchased the product accordingly. So it had been delivered in 2021, but as I spoke about, changes in the economic climate over 2022 into late 2021 into 2022 and throughout meant that they changed their focus away from this activity to production, and it was kind of out the blue they came back to us and said, can we go ahead and do the treatment during August 2023? So we suggested some QC measures to make sure that the fluids were still okay, which they turned out to be fine. And then the initial feedback that we've had is that the treatment successfully injected to the target zones this time, and we saw impaired injectivity during the tubing displacement stage. So following the first injection that we'd done, it's normally a two-stage injection that we do with a shut-in in between to try and maximize the scale formation that we get. So during the tubing displacement stage, it appeared that we'd actually managed to block the injectivity to the target zones. The first shut-in was followed by a successful pressure test for 30 minutes, although a slight pressure drop was seen after that. The decision was taken not to do a full second treatment, but they did target the annulus with part of that second treatment stage, as they believed that's where the pressure drop was originating from. And then another pressure test was performed and it held 670 psi for an extended period. I think they were talking 8 hours, maybe more, for that second pressure test. So the X-Max treatment has been injected to the target zone. This is the interim results that we've seen. A follow-up pressure testing is planned after an extended period. I'm not sure what the status of that is yet. I haven't been in touch with them to see. The initial feedback is that they had no change in the hold-up depth observed, suggesting that we did not scale build-up in the tubing as we have designed the treatment to do. The other things we note are that the time between supply and use of chemicals was greater than 2 years, and the basic QC performed indicated the chemicals remained stable and clearly still worked based on the other feedback that we've received, but we are still waiting on full feedback and final report from them. Next, please. So some of the frequently asked questions that we see, does the technology affect the well integrity? Well, the work we've done internally where we had is quickly represented on the right hand side there, where we filled a perspex tube with the fluid and left it for 3 days. And you see that the scale forms in a kind of spiral manner on the outside. It doesn't cause the formation of a big plug midway, and the scale that does form in there is quite soft and easy to remove. And the testing that the field test that we've done in Malaysia suggests that we saw no scale forming in the well based on no change in hold-up depth. A few of the other questions, I won't read them all, they're all there for you to see. So some of them are what the limitations on temperature at which scale will form. The scale deposition is expected to increase at higher temperatures as solubility decreases within decreasing temperature for the mineral being formed. In terms of decomposition temperature, the mineral scale that's being formed has a decomposition temperature of over 1300 degrees centigrade. So we don't expect limits on the temperature at which scale will form. It will just make it form more quickly. If we can, we like to have a little level of control or cooling as we do the treatment. But I know in obviously higher temperature reservoirs, the level of cooling that can be achieved with fluids as a pre-flush treatment stage are quite low. So we may have to look at the inhibitor that we use and make sure that it's suitable and capable of controlling the scale for a time at higher temperatures. One of the other questions I've heard asked when I talk about this is a loss of mass expected due to heating at 2 reservoir temperatures. There is a possible loss of water under atmospheric pressure, but in the field the mineral scale is formed in water at pressure. So at reservoir pressures we expect limited, if any, mass loss. Next, please. Some of the other questions that we get asked relating to the properties of the barrier once formed. Obviously, this is something that the operators and the regulators will be looking for us to answer. That's why we need a test. The testing that we're doing in Innotek Alberta is looking at some of this, but the way the scale forms within the pore space makes it more difficult to qualify the barrier compared to something like a cement plug, which you can physically have in the lab or create in the lab. That you can't create a physical sample of this, but the mineral scale has had testing done previously. That's what we're using to answer some of these questions. So permeability to gas. It's an inorganic crystalline mineral and it has low permeability, similar to cement. Do we see differential thermal expansion, for example? Well, the mineral forms under reservoir pressure and solubility decreases with increasing temperature. And the mineral itself has limited thermal expansion, similar to that of reservoir rock. Some of the biggest things we'll be asked are resistance, to reservoir fluids. And the testing that we have done, the mineral scale is formed, shows very low solubility in water, brines, acids, CO2, H2S solutions, and is insoluble in supercritical CO2 and hydrocarbons, which is why we think it's a good barrier. Next, please. So the way forward, we look to continue developing the test methodology and establish our in-house core flood capability, because that's obviously the final qualification test that most people are going to ask is, here's a bit of our core, can you block it? So I think that core flood capability is essential. We will look to do further product development and optimization once we learn more from the field and once we learn more about the chemistry in the core flood testing that we can do. I'm looking to identify gaps in product testing to date and confirm suitability for specific applications. So we've only looked at sandstone at the moment, so there are other rock types obviously, and then loads of variations on sandstone. So can we look at the permeability of the rock? Does that have an impact on how quickly and how well its scale forms? So those are the things we need to look at in the core flood, for example. As I say, I'm going to look to work with independent third parties to investigate and establish industry accepted barrier qualification protocols so that we can get the regulators buying in. So, the Texas Railroad Commission, etc. in the US. The OEUK have already added this as a barrier, an accepted barrier method, not specifically naming exclude, but using in-res information to their decommissioning guidelines. We'd look to progress the ongoing or planned field trials, obviously looking for interpretation of results, feedback from the customers. We need to act on lessons learned, so further product development may be necessary. It may be just down to treatment design and the protocols, how well they work offshore and how easy it is to pump. And then we'll look to prepare and share full case histories. And we're also starting to talk to as many regulators and country and state regulators as we can to obtain approval for exclude as an acceptable barrier, and then to obviously to find out what we need from to show them to make that happen. Next, please. And I'll happily take any questions that have been asked throughout.
Thank you, Mark. Very interesting. We're going to try to stay on schedule here, but we have time for a couple questions. So there's two from Carl Dick and Henry Monpetit, who are both wondering about thermal well applications. So you touched on some of this with the stability of the precipitated high temperature, but for SAGD or steam flood applications, can you expand on the placement and control of the reaction, and then durability of the material in, say, 100, in the range of 150 degrees C to 240 degrees C?
Yeah, I mean that's going to be a challenge for us. The higher temperatures. I can look at the inhibitor. I haven't had a chance to do so yet. I think the inhibitor, we have inhibitors within Itomatch that are easily suitable for controlling scale at that temperature, and will be stable. It's about placement will be your challenge. And once these inhibitors start going into the reservoir, they start absorbing. That's kind of the process of the control that we have is the scale inhibitors in the solution until it meets rock, and then it starts to absorb, which means that the scale is then free to start forming, which will give a challenge for placement. It's not a problem when you're talking about it for a barrier solution, as you want to, have that barrier placed from the near wellbore out to a desired distance. If you're looking at for some of these other applications that you mentioned, you may be looking to try and use it to direct fluids. So you may be trying to place it in specific areas and zones within the reservoir, and that will be your challenge. But it's always a challenge when you're looking to place something into the reservoir. And there are ways and means we might be able to do that, but we're not very far down that road yet. Looking at this, and that's where core flood may come into its own, and we may be able to selectively place and get the scale to form where we want it. But that's something for down the line, I'm afraid, at this stage.
Excellent. So I think we will have to move on to our next speaker, but thanks very much, Mark. Very interesting.
Thank you.
So our next speaker is Peter Knight from WACORP. And I'll hand it over to him now.
Good morning and probably good evening in some places here. My name is Peter Knight. I'm president of Wireline Abandonment Corp. Our technology is a process change to how you would pressure test downhole barriers. If I could go to the next slide, please. So what our tool does is we have our own packer and setting tool and pump incorporated into it. If you want to press play. And then we have gamma ray pressure and temperature, annular and internal into the tool. We run into the hole. We log onto depth, and then we anchor our packer. It's kind of slow here. We anchor our packer. I'll just wait. So yeah, we take fluid depth too. The tool is balanced to the hydrostatic in the wellbore, allowing us to set and pressure test above the differential of the fluid in the hole. We can go to the next slide. That's okay. Yeah, so the system in operation, the way that we control the tool is through a valve manifold, where we send a command from surface. So while we're running in the hole, we're in the running hole position, and then we set the packer, and then we set the plug. If you go page down. So the way that we manage the test is we need fluid in the wellbore around the packer and the plug, and then we use either the onboard fluid system or the wellbore fluid to initiate pressure. Page down. That fluid comes in, it's drawn in through the pump, through the check valves. Page down, please. Through the check valves. Page down. And then there's a inline pressure transducer. That one is reading everything that the tool is doing down the hole. So we can see the packer set, we can see how much pressure we have in the packer. If you page down again into the valve manifold where we control the tool. So our first step is to set the packer, page down, and then we set the plug, page down again. And then we test we test the fluid between the set packer seal and the plug seal, or if there's an existing barrier, then we set the packer above it and we just energize the fluid that's in the wellbore against there, and we can read it out live on surface. If you go page down, please. So technology overview, run the tool into the well, gamma ray collar log into position like normal, set the packer slips in your seal, set your plug, energize the test between the plug and the seal. In order to do this, because we're testing at the target, we actually generate the entire wellbore column if the fluid is not surface to simulate a surface test, and then we add 7 MPa or 1000 PSI and hold a stabilized test for 10 minutes. We release the tool pressure and then we release the packer pressure and come out of the hole. Immediately on surface, we're going right into cementing operations, grabbing the baler, and then back into the hole if we have more than one zone or formation to abandon. Page down, please. Surface testing can get fairly complex. There's a lot of issues that affect your test pressure and a lot of questions that you may have sometimes when you're losing pressure, including tubing leaks, wellhead leaks, temperature changes, casing expansion, along with fluid volumes. I've been on location where they were calling out for casing inspection tools because they thought that the well was leaking, but they had actually not pumped enough fluid into the wellbore. And it was corrected, but it took a lot of time to figure that out. This technology tests right at the target, eliminating all of these variables that you normally find from a surface test. Page down, please. So AAR Directive 20 is where we came in with the technology in 2018, requesting a pilot to prove an equivalency to a surface pressure test. The regulations requires that once the bridge plug has been set, it must be pressure tested to a stabilized pressure of 7,000 kPa for 10 minutes. Nobody really knew what a stabilized test looked like, and once we had this data, we were actually able to show a stabilization trend. We went forward with this where we set all the plugs in the well, including the top zone, and then we recorded the surface test and plotted it and charted it to show the comparison between the stabilization trends of our technology and the stabilization of testing at surface. Page down, please. So you can see on the right side in track 3 and 4, the blue dash line is your wellbore hydrostatic, and on the right side is the pressure that we're generating with the tool. On this one, we generated 22.6 MPa, and then we start the stabilization trend. So you can see it starting to drop as it goes down, but it's maintaining pressure. And what we showed the regulator was all tests are going to show a stabilization trend. How much is acceptable? What does it look like? Are all shown on these for every test that we do. Page down, please. So you can see here, this is a surface test with a full column of fluid, but they get the same signature where the pressure comes up and it begins to drop. It always continues to drop slightly. You won't ever hold a zero leak off test unless you have a temperature change. So if you go down a page, please. Here's one that I was talking about where you have a change in temperature. We were on this wellbore, it was minus 29 degrees Celsius on location. They had steam on the wellhead. We had the pressure transducer landed in the wing valve of the casing valve. And you can see that the pressure is increasing as the temperature is dropping. This was an accepted test due to the increase in temperature, but not really the results that you want to see when you're trying to prove that you do have pressure integrity. Again, suggesting that the variables on surface make testing a little bit more complex. A page down, please. So what does a stabilized test look like? Here's our test right here. This is recorded over 10 minutes, so I just spliced them together. You can see on the right side again that we started out at 22.2 MPa. This plug was set at 1,360 meters, and then we ended the pressure test at 22.1 MPa. Next slide, please. So here's a failing test. This wellbore didn't have the best prep. We ran into the hole we tagged high with the gauge ring. We had to beat through it. Where we set the plug was in the area where we were having difficulty getting through the obstruction. We started the test, and you can see on the right again where there's a blip. It starts to fail, and then it continued to bleed off where we couldn't hold the pressure. Fortunately for this technology, we were able to just pull out of the hole and run a new plug and set it above it and have a successful test, carry on and make sure that the wellbore has integrity at the point of abandonment to reclaim it. Next slide, please. Next slide. Page down. Our pressure transducer has a range from 2 to 100 MPa. The resolution of the scale is 0.1%. So any fluctuation of 0.1 MPa is really negligible data. If you want to page down again. And then we're taking 25 samples per second with a 16-bit digital signal processor. Page down. And then our supply, power supply voltage is 5 volts, so 5 millivolts is equal to 1 MPa. And again, changes with 0.1% of the full scale. Page down. Page down again. Yeah, so here this was a shallow well at 494 meters. When we're testing, we're not testing the entire wellbore. So we have a very small volume, which gives a very high resolution to the test. So we had 12.5 start to 12.4 MPa. Page down. And then if you carry that into this equation, page down again, 0.1 MPa lost at that volume is 0.4 milliliters or 8 drops, 50 microliters. Will change that pressure. Page down again. Temperature change. What's it really going to do to this tool? 0.2 degrees change in temperature, page down, equals 0.1 MPa. This is seen commonly, especially in wells where they're torquey. They've been suspended for a long time, where we have to pump cold fluid from surface while we're testing. We can get an increase in temperature just from the geothermal gradient warming up the fluid in the wellbore, which changes the pressure reading on the tool. But as it's done, it's understood. Page down. Casing expansion. If we're not supported, we're going to change our volume again by about 11.6 milliliters. This is for 4.5 casing, where we're energizing to 6.9 MPa or 7 MPa for the test. And then the distance on the tool from the packer element to the plug is 2.54 meters. Page down, please. So what's it good for? It's good for wells like these where you've got a real tight perf interval to the lower zone that you want to abandon, where you don't want to get caught in a existing collar, and you need to precisely locate your packer and test and get all the data that you need without running into any issues with stuck tools. So our gamma ray and our collar locator are key components to a successful job here. Page down. Water shut off. If you got zones that are making water, we can go in, set a plug, have it pressure tested. It's done. You don't have to ever worry about it again. Make accurate depth control, increase your production, all the good things that you want to do with your technology. And page down. Cement retainer squeeze. This is becoming extremely popular, especially in deeper wells. We're running it off of the rake. We're just wireline setting the retainer with the tool, and then we're pressure testing it. So we're proving that they have pressure integrity, and then they're able to go in with the stinger, latch in, pull neutral, pressure test the string, and then they're able to do the cement squeeze. Multiple well campaigns. If you want to have your well bores ready to go before your rig gets there, here's a great way to do it. And if you just want to save time and save money, here's the way to do it. Next page. Existing barriers. So if you have a plug set in the packer, you can run down at any time. Set this tool and pressure test that and prove that you have wellbore integrity. The test is almost instant. We get up to pressure in about 5 to 10 minutes, and then we're reading that out on surface. We give you a digital record of the test, and away you go. Next page, please. Reverse pressure testing. This is conceptualized with the energy regulator here in Alberta. And what we're doing is, if there is retrievable systems in the hole, there's no way to prove if it's holding pressure integrity that your redundant plug is holding. So what we want to do is kind of in the middle there, where we trap pressure above the packer and the new plug, and then we bleed down the wellbore pressure, and we're looking for a response to that. We've discussed how to do this. We're setting the plugs a little bit higher than we normally do, and that allows for the volume needed for the tool to see the pressure change. But as you can see from the slides before, it takes minimal temperature, pressure changes to influence the data that we're recording with the resolution of the tool. Page down. So again, your wellbore program, if you can, bleed off and kill well. Chunk basket gauge ring, K-watt, and set and pressure test the plug, and you'll dump bail. And then your top zone, you need full wellbore integrity, so you will set that plug with your Baker tool or equivalent, and then you're going to pressure test from surface, and then you'll dump bail. If it's a super torquey well, if you're making gas, multiple kill attempts, we recommend just setting the plug, and then we can run down and test on top of that plug, but still save you a ton of fluid and time that you would spend trying to kill. Next slide. So conventional zonal abandonment, it's just big. It's a large footprint. It's inefficient. You're going to use a lot of fuel. You can need explosives with conventional tools. You got heavy vehicle traffic around area residents and a lot of noise pollution. We can go out there with just a mast unit and a pressure truck and finish this job off in a single day where it would normally take you a zone per day. A lot of time spent that you don't need to anymore, and a lot of savings and emission reduction and noise at the same time. Page down, please. So emissions reduced by the process change. Running this tool, we can look at over the road consumption. If you're moving a full service rig and you're going to travel about 2 hours, you're going to burn about 600 liters of fuel. If you're moving your wireline unit, your pressure truck, and your 2 pickups, one for the client and the wireline crew, you'll burn about 184. On-site consumption, if you've got everything there operating, you're burning about 48 liters an hour. This is for hot and for cold weather. You need to keep your systems running so that they don't shut down or freeze up. We burn about 12 liters an hour with that equipment on surface. Next slide. Safety incidents. We're also reducing the number of people on the location, and we're reducing the number of days. So we're taking it from 8 people down to 6. The way we're operating now, we're even able to drop another person, so we're taking it from 8 to 5. And then days to complete, this is just a 2 zone. We're going from 1 full day to a half a day. Less hours means you're gonna have less incidents. It's a perfect way to demonstrate the safety risk triangle with exposure hours on surface. Page down. Testimonials. Yeah, this is actually our first job. We ran it with Shell Canada here. And on that job with the original prototype tool, we saved about 10K or 30% of what it would have cost to normally abandon this well. Next slide, please. And this is what I was talking about with the running the cement retainer. We do this for crew all the time. We save them about 8 grand every time we come out there to do that in a half a day's time. Page down. That's my presentation. So I'm excited to answer some questions. I apologize for the video lag there, but if you need a copy of the presentation, I'm hoping that we can deliver that to you.
Excellent, Peter. Thanks for that. And also apologize from our side for the technical difficulties on that video. We have a question here from Trevor Alescu. How does the KWAT tool perform in extended reach wells with different casing sizes and liner hangers? Any issues or limitations?
Yeah, the tool is casing size specific. So we have a 4.5, we can run in 5-inch and 5.5, and then we're building up to 7-inch. So if we have to change casing sizes, then we would change out the packer parts. There's only 5 parts to change out on the tool. It's on the lower end, and then it's the same tool string that goes in.
And what about deviated wells?
Deviated wells, we can work up to 30 degrees, no problem. If it's a vertical deviated, it's easier. Slant wells, because it's a sliding, it's a reciprocating pump, so we have to be able to drive the pump back down. If we've got excess line friction, then that becomes a challenge.
Cool. I have a question. So my understanding is you can pressure test with the wellbore fluid or fluid that's contained in the bladder.
Yeah.
What is the advantage of each, and how's that decision made?
So the tool does it naturally. It'll initially take it from the bladder, and then it takes from the wellbore if we need to. We still need fluid in the well where we're testing around the packer. So this is where it's drawing into the pump itself. The advantage of the bladder is if there is gasified fluid, problems in the hole, energized energized wellbore, it's going to take from that wellbore and allow you to make the test, or sorry, from the bladder. It's just a control method that we've learned through the design that we needed to carry clean fluid in the tool based on well conditions.
Yeah, that makes sense. We have one more question here from Trevor. No issues requiring pumping down to pass through the liner hangers as compared to running in with tubing.
I think he's talking about like a horizontal well. Is that correct?
Yeah, that would probably be my guess. I don't know if Trevor, if you want to elaborate, but yeah.
So we are designed for vertical application. So yeah, we can work in a high deviation, but pumping the tool will not allow you to cycle the pump. So in those applications, I would recommend like coil.
Yeah, just a clarification here. Yes, extended reach horizontal wells with such as which we are seeing in the Liard and Horton River.
Yeah, we won't be able to do that. We could test down to the heel. We have ran tests. This is an interesting well. We did it for harvest about a month ago, but we landed the packer in the vertical section above the below the existing perforations at 2850, and then we tested a plug that was down at 3178. We have pretty good wellbore fluid, so it didn't take a whole lot of time to get up to pressure, and we were able to give them very good test results with that.
Great. Well, thanks again, Peter, and I think we'll move on to our last speaker today.
Great. Thank you very much.
So our last speaker is John Griffin from BioSqueeze, and I'll turn it over to him now.
All right, good morning. I'll go quick so we stay on schedule here. Yeah, so a little bit about BioSqueeze. We're a biomineralization technology company, and really we got started 2011, 2012. Keep jumping around there a little bit. Yeah, so we actually got started with a grant with the United States Department of Energy. And sorry, we just keep going back and forth for some reason on the slides. We got started with a grant with the United States Department of Energy to come up with a microbial solution for repairing damaged cement and microannuli on deep geological CO2 sequestration wells. We basically became BioSqueeze Inc. in 2019 when we commercialized this technology and began sealing our first wells. We've sealed a little over 100 wells to date. Since 2019 across the U.S. and now in 2 provinces in Canada. We have 4 operation facilities. Currently, we have a shop in Red Deer. We're looking to expand soon to Edmonton and then further northwest to keep supporting all of Canada. We've introduced this technology to a lot of regulators throughout the U.S. and in Canada. And to date, we've been endorsed for use by every regulatory body to date. Speaking in Canada, we've presented to Alberta, BC, and Saskatchewan, and we've been actively working with Alberta primarily, which has been great to work with, and the AER and collaborating on a lot of wells together. Next slide. As most on the call are probably aware, vent flow is a challenge. Vent flow is a challenge, and it really initiates as wow, this is challenging here, guys. As you have unwanted influx of wellbore fluids migrating into the annulus. A lot of this is debonding from the casing or the formation wall of the cement and very small leakage pathways inside the cement. Many of these are the thickness of a human hair follicle, maybe 60 to 80 microns. As a result, a lot of attempts to date sometimes are not always successful and become very expensive and repetitive trying to solve the problem. And this is where, we'll talk to you today. These are the wells that we have been specializing in and focusing on is wells of this nature here, where there is comparable cement behind casing, as this technology is not a replacement for cement, but it's highly effective and has had unprecedented success at repairing damaged cement and restoring its bond to casing and or the formation and providing wellbore integrity. Biomineralization is just a process in which a living organism produces a mineral. The mineral that we are producing is crystalline calcium carbonate, okay? So biomineralization is natural in nature, and what we are doing is we're taking this natural process and we're accelerating it very, very rapidly, okay? So the bacteria itself, it's non-pathogenic, meaning it causes no harm to human life, even somebody with a severely weakened or compromised immune system, okay? This bacteria can be found in the human gut, it can be found in the soil, so it is naturally occurring. What we're doing in these wells is we're creating a biofilm, okay? Biofilms are usually a nuisance in almost all aspects from manufacturing and industrial processes. We all go to the dentist hopefully every 6 months to get the plaque scraped off our teeth because that is a biofilm. The good thing about this biofilm that we are precipitating is it's very sticky and it readily adheres to rock, cement, and steel, making it great for bonding to the formation, bonding to the cement itself and the casing. The end result is it's a natural process that can be sustained in a variety of temperature applications, currently up to 76 degrees C and a pH of 5 to 11. But we create a, same molecular composition to limestone, which is a natural cap rock. There's a lot of advantages to this technology and fluid system, but the three primary ones are penetration, that it's self-diverting, and that it's impervious to gas cut. So starting with the first one, a fluid system's ability to occupy a pore space or a crack in cement comes down to two variables. The first of which is the viscosity of the fluid system. This fluid system maintains a low viscosity for the duration of treatment, barely over the viscosity of water at 1.05. The max particle size is 1 micron. So we are able to access pore spaces very small. And to put this into perspective, some of these cracks are 60 to 80 microns in size in cement, which is about the thickness of a human hair follicle. Because we seal through injection, we don't spot and wait. This is not a spot and wait fluid system for a reaction to occur. We seal through injection on the fly. And because of this, we reduce the permeability of any pore space the fluid system occupies. As you keep injecting, the fluid will keep taking the path of least resistance. So an inherent feature is it self-diverts through injection. The last is it's impervious to gas cut. So while our industry is used to things like cements and resins, things that thicken with time, things that harden with time, things that have a limited pumpable window, and we are dependent on them to reach a gel strength before they are gas cut. This technology is very different. It is a biomineralization technology. It grows with time. So we grow crystals and they precipitate from a liquid that's injected. And the way they precipitate is very similar to the way plaque grows in our arteries. So if you look at the animation in the top right, you'll see it looks like there's deposits accumulating on the outside of the wall, and they keep accumulating and growing layer upon each other until you choke off the leakage pathway. Similar in our arteries, where it eventually chokes off and prevents the flow. The end result is a molecular composition same as limestone, right? Very strong, significantly stronger than the Class G cements our industry is using today. The other neat attribute is this technology doesn't require drill out. So it goes into perforations or cuts or notches made in the side of casing, and the wellbore is left full ID. So we're often running retrievable bridge plugs below biomineralization, jobs, and we're going and we're able to pull the bridge plug immediately after. There's no drill out. The casing's left full ID. So you can take a difficult well that is a surface casing vent flow. You can solve the surface casing vent flow problem, and then it becomes just a straightforward abandonment. Shown in the top right is a before and after treatment ultrasonic log. Pink represents microannulus, blue represents liquid, gray, dark gray, or black represents solid or cement. So for this specific well, we did a perf and squeeze at 2880, and you can see over 70 feet of annular space filled as we show up as cement on a bond log, as cement and limestone show up as the same. So you can see that the void spaces were filled, and what's left is solid crystalline calcium carbonate, and this well was sealed. So I'll go through a little bit of the launch of BioSqueeze into Canada in Q1, and then we demobbed during breakup and came back here in Q3. So as far as the commercial launch, we brought up a second gen unit mid-January and began working on wells late January, really far remote BC. The scope of this was to strictly focus on wells with surface casing vent flow and or gas migration, and a lot of these wells were very difficult, right? BioSqueeze was not the first attempt. We were the 6th, 7th, 8th attempt on a lot of these wells. During Q1, we worked on 6 wells. Some of these wells we squeezed from multiple injection points depending on the feed rates, and then the results are shown down below. So the first well we actually mobbed onto was a complete success. We eliminated the vent flow. The second well, luckily I got to use this presentation. I got a call last night. That well just passed a bubble test. So the second well we did in Q1 just passed a bubble test because it took that long to vent off. Wells 3 through 5, we did see impacts and changes to the vent flow, some more than others. Some we ran post logs into to evaluate to see how many meters of coverage was obtained in terms of crystalline calcium growth, but we're still monitoring wells 3 through 5. Well 6 was a blind gas migration squeeze. This well was done with the ground completely frozen. We had no indicator to measure on surface or monitor the impact, completely blind. Post-soil samples afterwards showed a 72% reduction. Unfortunately, we were cut short on this job. We wanted to stay out 1 to 2 days longer, but the ground was literally, melting as we spoke. So we had to demob off location before we wouldn't be able to get off location. So Q3, Q3 we brought everything back after breakup and after monsoon June, and to date now we've done 6 wells in Q3. The first 3 wells were slam dunk success. Clients were all extremely happy. The 4th well, also very happy. This well, we reduced the shut-in pressure by 99%, and it's now on long-term monitoring. And the flow rate we reduced by 95%. So this well, similar to a well from Q1, we think it needs to vent and degas for a period of time. Then we had a couple wells we were not successful on. The 5th well, we found out after the fact, looking at an open hole neutron porosity, we're actually pumping into a coal seam. So we're pumping into a very porous interval where gas was able to circumvent. We weren't seeing a typical treatment on surface of what a normal well treats. So we're working with the operator for well 5 to go back and select a different interval across a tighter shale or a cap rock. Well 6 was actually just recent. That was last week. This well was also unsuccessful. We could see impact the vent flow when we pressured up to inject. However, we were not allowed to go over 0.9 frac gradient for this operator. So we unfortunately were unable to inject fluids and to repair the cement. So some of these inconsistencies has really, made us rethink our process. Everyone wants to claim they have a 100% success rate. The truth is we can't always be successful. And a lot of success is dependent on, for these technologies, that they're utilized in the right wells for the right application, for the right purpose, and really at the right depth. So we realized very quickly after Q1 and then coming into Q3, we really need to implement a world-class improvement in the way we review wells and the pre-job analysis and the candidate selection performed. So we now do a much more thorough review of casing bond logs, and we now reprocess those bond logs ourselves using raw and segmented data. We do a lot, significantly more thorough review of the geology to understand the cap rocks, looking at open hole neutron porosity logs to understand what's the porosity around us, where can gas potentially circumvent, how much likely storages are above us, and then gotten even more specific with reviewing carbon isotopes, not just to databases, but now finding nearby offset producers that we can get gas samples pulled from, where we compare the gas analysis to really truly identify where is the source so that we can ensure that we're at or above the source. Currently, we're mobilizing another unit. It's already in Canada, so we've already expanded and added an additional. It's our new 3rd gen unit, which has a built-in bioreactor on board, so we don't have to ever worry about running out of fluid during treatments. So a little bit about the design process. It's a typical information gathering. It starts with wellbore diagrams. It moves on to getting cement bond logs, reviewing any type of meter or vent meter type technology on surface, and reviewing the impacts to the gas flow and the surface casing vent flow through the history of prior interventions on the well. We also look at any noise acoustics, neutron porosity, and we reprocess a lot of the cement logs that we do today, every single one that we can get the raw and segmented data for. And that helps us really finalize our depth recommendations to client and helps us with the selection of the treatment for the downhole squeeze. Here's an image of the ACI. So one of my favorite quotes is, despite its potential, the cement bond log is probably one of the most abused, misused, and misunderstood logs used in the oil field today. Miscalibration, inadequate information, and a severe lack of standardization are enough to push petroleum engineers into a morass of bewilderment. It's amazing that you can run 2 bond logs sometimes, 2 different vendors, and it's the same exact tool and the same well on the same day, and the logs could look slightly different. So to make sure that everything is starting from zero on the same playing field, we take the raw and segmented data and we process these waveforms. We break up the annular space behind the casing into four segments, and then we break those segments out and analyze for channels. So for this well right here, we actually know that there is more of a channel and micro annulus closer to the formation. So the cement is debonding more so from formation. As you see formation arrivals in column 15, you can see a channel that's migrating and channel in segment 13 and 14, right? So this helps us identify also perforation recommendations, how to intersect that channel, because we can't be successful in sealing off vent flow unless we access every leakage pathway that gas is migrating. So in addition to doing field trials, we've done Initech testing, which we're grateful to participate. It's been wonderful working with Jonathan and his team. So the testing, involved pumping through, apparatuses. Now, a lot of challenges came up as a lot of these tests were originally, they're very, very short. Okay, and our technology is typically deployed in a well where we create a tortuous path and a seal over a long distance, just like the graph I showed prior where we created a seal over 75 feet. So it's very difficult by nature to do this across a very short apparatus, especially one that's about 0.5 meter in length or shorter. Also ran into some issues with the scaling of valves and equipment. As we are often exceeding frac gradient to squeeze fluids in initially, precipitate the calcite, allow that pressure to bleed off and relax so that when it does close and there is a closure force, now that you have crystalline calcium carbonate that has created a blockage, so to speak, to prevent this gas from migrating. So it's very difficult to sometimes replicate a lot of tests that are historically designed for technologies that harden with time, thicken with time, with a technology that scales or precipitates solids from liquid. So definitely have had our fair share of some challenges, but we're still working within Inotech and look forward to future collaboration on how we can take some of our success in the field and recreate it in a lab. So we're very tight on time due to some complications, so I will fly through this so there's time for questions. So this was actually the very first well we did in Canada. This was a well in BC. This was a well that they had surface casing. The well was never put on production, but it had a vent flow. They had done multiple cement retainer squeezes in this well, and they ended up prepping this well by drilling out all the cement retainer squeezes, and then we ultimately did a bio squeeze in between two previous cemented retainer zones prior. So here you can see we ran a retrievable bridge plug, did a perforation, and ran in on a work string with a tension set packer. The purpose of the packer and the purpose of the retrievable bridge plug is just to compartmentalize where we're going to do the injection. This prevents fluid dilution. It also prevents us ballooning that casing string, so we don't artificially bridge off the microannulus that's allowing the gas to migrate. Prior to this well being biomineralized, it had a melted alloy used prior to biosqueeze, and which is why biosqueeze still got the opportunity to come in after that did not work. So this is what the treatment looks like. So when you are precipitating a solid and you are injecting it out of a liquid, and that liquid maintains the same viscosity, you see a few things. One, you will see while holding a constant pressure, you should see a decline in injectivity. So what we're measuring on these jobs real time on surface is how we are actively reducing the injectivity into the interval real time. So we step up pressure, we hold a constant pressure, and what we hope to see is a decline in injectivity. So in this graph, pressure shown in kilopascals in red and shown in green is our injection rate in liters per minute. So for this well, we stepped it up to 3,300, rate dropped from 0.23 liters to 0.12, so still a lot of fill up, 160 liters we squeezed, and this is over 6.8 hours. So this was really just day one. So this is the two intervals we pumped in day one combined into one graphic. So we see some reduction in injectivity, but nothing crazy. So now day two, and one reason we pump 12-hour days is so that the biomineralization process can continue overnight, and then we resume the operations the next day. So day two, we start seeing significant decline in injectivity. So you can see we keep stepping up the pressure to 3,300 every sequence, and we had roughly a 74% reduction in injectivity over the course of this day while holding this constant pressure. So significant improvement, and you can see we're getting down into 0.1, 0.08 liters per minute. So when you are repairing damaged cement and you're repairing cracks in fractures in cement that are the thickness of a human hair follicle, 60 to 80 microns in diameter, you're going to be pumping at fractions of a liter per minute. You're not going to be pumping at cubes per minute. So we go to day three. Day three, we reached a final injection rate of 0.04 liters per minute. We had a 78% reduction this day, and we keep reducing the pressure as we are sealing the well, right? So day three, we hold a constant 2,100 that whole day. This well, this day, lasted only 5.5 hours of total pump time and only 26 liters, right? So very little is injected over a decent amount of time. But you can see the final injection rates we achieved 0.04 liters per minute. So very happy with the results. So what you monitor on a biomineralization treatment is you are monitoring with a constant injection, what is your initial injection rate and what is your final injection rate? How much are you reducing the permeability of that zone? You also have to take into account What is the frac gradient at that interval? You know, it's a lot harder to sometimes to get a car rolling than to keep it rolling, right? It requires a little bit more force. So often we're stepping over frac gradient just to establish that injection and that initial injection, but then we're tapering it down. And what that does is it allows everything to open up and to push the fluid in so that as you precipitate solid calcite, essentially you relax that pressure off. It now has something to close on and pinch off. And that's it. I tried to fly through it as fast as possible given the complications.
Yeah, thanks, John. Again, sorry for the complications, but we do have a few questions here. So again, another question from Trevor. Can this be used for base of groundwater isolation prior to cementing on casing strings with a limited bond? I'm not sure if he's talking about a surface casing interval with pour cement here, but.
Yeah, so if there's, you know, we'd have to approach the AER with that question, which is a, you know, great question. I would, you know, we are using this actively in the US above basic groundwater, at basic groundwater, even injecting it into oil and gas wells where the oil and gas is actually leaking into aquifers. So this is being used in that application. Now, what is required is there needs to be something behind the casing. So it sounded like the question said prior to cementing.
Yeah, that's what he said, and he did clarify here with at the surface casing or just below the shoe, plus or minus 30 meters. So.
Yeah, so we've done it both in the States, and we're working with the AER currently on case by case, obviously, as it's non-routine in Canada. We've done several wells above basic groundwater. As long as there's cement behind the casing string in question, then biosqueeze is a potential solution to solving that problem.
And a couple questions here from Trust and Progress. How close to the squeeze zone can you perforate after pumping your product?
Say that one more time. Sorry, Jonathan.
Yeah, how close to the squeeze zone can you perforate after pumping your product? Any limitations?
How close to the squeeze zone? So if we squeeze through perforations with biosqueeze, those perforations are still open. You know, we will reduce the permeability of the perforation tunnel, but most operators are spotting cement across that afterwards to create their barrier, so to speak, inside the wellbore after the vent flow is eliminated. I don't see any challenge at all with perforating where we've biosqueezed, as long as they don't try to break things down and create more fractures.
Yeah. And then are there any restrictions in regard to the bottom hole temperature or issues with surface temperature such as negative temperatures?
Yeah, so I don't know if you could see from the pictures on the previous slides, but it was definitely negative when we pumped the jobs in BC. Those roads were winter access only. To combat cold climate temperatures, obviously we just steam wrapper lines and do what we can to prevent water from freezing. So as long as water is not freezing on surface, then you know, if it's weighted up 5% KCl, it's not a problem. Higher temperatures, yes. Currently, there's a limitation of about 176 degrees Fahrenheit, or sorry, 170 Fahrenheit or 76 C. However, it's not been an issue to date in all the wells we worked on in Canada, as we're solving the vent flow at depths above the formation that's been leaking, and we have not ran into any temperature thresholds to date there. We are looking at aligning with some operators to deploy this in SAGD assets. So for those, it's still a case-by-case basis looking at the wells. We would look at deploying the technology above where the steam chamber is and restore wellbore integrity across the caprock above the steam chamber, if able. If not, we have a high temp version of this technology. It's still in R&D mode, but it's getting close to commercial deployment, and it works in applications over 105 degrees C.
And I think we have one more question here. It's pretty straightforward. Is this approved with the Saskatchewan regulator, the Ministry of Energy and Resources?
It is. We've presented to them. They have had no no buff to it. I mean, they really like it. So no issues with Saskatchewan.
Excellent. Well, we're at 11 o'clock here in Alberta, so I think we'll wrap it up there. Thanks again, John. Very interesting. Nice to see those case studies.
Thank you, Jonathan, for the opportunity.
So yeah, we'll wrap up here. I'd like to thank everybody for attending the webinar, and especially our speakers for volunteering your time. I'd also like to thank our communications department here at Innotech and Sticks and Stones here in Edmonton for all their help and work setting this up. So as I mentioned at the beginning, we are planning one more webinar on October 31st. We expect to have 4 more speakers there, and we'll be posting a registration link with more information very soon. And with that, thanks again to everybody, and we'll adjourn.